Good day, everyone. I am Mary Joy Almasin. Today, we're going to discuss the generative grammar, rules, and description. Also, we're going to discuss the judging the adequacy of a grammar, finite state grammar, rewrite grammar, phrase structure grammar, and the last one is the adequacy of phrase structure grammar. Now let's start to the judging the adequacy of a grammar. So the main goal of grammar is to describe how native speakers create and understand sentences and in their language. For grammar to be effective, it must be clear and comprehensive. Now let's break down the requirement for what makes grammar adequate. So the first requirement is the explicitness. Clarity, the rules of grammar should be straightforward. If a rule is vague or can be interpreted in multiple ways, it does not provide adequate guidance. For instance, vague definition, saying a noun is a name of a person, place, or a thing. It's not specific enough. It doesn't clarify cases like you, which can be a noun but doesn't fit neatly into that definition. So that is vague definition. Let's go to preposition. The rule that preposition always come before noun is misleading because it doesn't account for cases where they appear elsewhere, such as in question or relative clauses. Example, what are you talking about? Next, falls in explicitness is coverage. Grammar should be comprehensively address all possible structure and expectation in a language. If a grammar ignores certain sentence, type, or construction, it fails to provide a complete picture. For example, negation, how negation works in sentences isn't always clear in traditional grammar. The next one is the non-finite clauses. These are clauses that do not have subject and a verb, like to eat in I want to eat. Traditional grammar often doesn't cover this at well. So that falls in the explicitness, the clarity, and the coverage. So the first requirements for what makes grammar adequate is the explicitness. The second one is the full explicitness requirements. In generative capability, observational falls there are two: observational adequacy and the descriptive adequacy. A grammar is observational adequate if it can generate all the grammatical sentence of a language while also identifying which sequences are not grammatically correct. This means it should cover a wide range of a sentence that speakers might create. Descriptive adequacy. For grammatical sentence, the grammar should provide a detailed description of its structure, indicating how the different parts relate to each other. This includes identifying the rules of each word, like subject, verb, object, and explaining how they interact. So that are the two requirements for what makes grammar adequate. The first one is the explicitness, and the second one is the full explicitness requirements. In explicitness falls the clarity and the coverage, while the full explicitness requirements involves the observational adequacy and descriptive adequacy. Now let's proceed to generative grammar. Generative grammar proposes a systematic approach to meet these requirements. It uses specific rules and structures to describe how sentences are formed, focusing on syntax, the arrangement of verbs in sentence, and rules defining how different elements can combine to create a valid sentences. So, historical context. Some linguists before the rise of generative grammar tried to create more precise system. So in Jesperson, his work analytic syntax used formulas to succinctly, correct me if I'm wrong, describe English syntax. However, the relationship between the different labels like subject or object were not always clear, making it difficult to apply his system universally. And the second linguist is the Harris. He developed equations to present how constructions are formed. For example, his notation shows how a noun can be constructed from other elements. For example, equation N1 S equals to N2 means that a complex noun N2 can consist of another noun. Noun 1, example equation noun 1 minus S equals to noun 2. Noun 1 minus sentence, S means sentence, I think. Noun 2 is equals to noun 2 means that a complex noun can consist of another noun 1 plus a plural inflection. This highlights how different parts work together in forming valid structures. So, critics of Harris' approach. While Harris' formula brought some clarity, they also had weakness. Classification. Some syntactic categories were not well defined. For instance, he didn't categorize verb as transitive, verbs that take two objects, or distinguish between countable and uncountable nouns adequately. Next is morphological variation. He didn't fully address non-productive construction like in large but not in small, meaning there were limitations in how he handled word formation. Sentence pattern. In important constructions such as passive sentence, example, the book was read by her, were not adequately explained in his system. So that so in summary, to judge the adequacy of grammar, both observational and descriptive adequacy are considered. Phrase structure grammars are a foundational model but often need to be supplemented with transformation. Again, to judge the adequacy of grammar, we both apply the observational and descriptive adequacy. Now let's proceed to the finite state grammar. So what is finite state grammar? So a finite state grammar is a simplified model of grammar that operates using a finite state machine. This means it has a limited number of states and it moves from one state to another by following certain rules. The rules dictate what word or symbol should come next in a sentence. Finite state grammar are built on a model called Markov process, which is used to predict the next word based on the current word or state. This process is named after the Russian statistician Andrei Markov. So in this case of finite state grammar, each word transition is determined by what comes directly before it, making it a step-by-step transition through a series of states. So that is a finite state grammar. So how does finite state grammar work? So here, states, think of these checkpoints in the sentence. So state means think of this as a checkpoint in the sentence. For example, starting at the first state, you choose a word like you. So that is the states. That is the checkpoints of the sentence, which is in the given example, we choose the word you. Next is transitions. These are the rules that move the system from one state to another. If the first state is you, the transition rule might say go to the next state when the word is bright. So this again, how does finite state grammar work? First is the states. So we choose the word your. Your. Next is transition. If we say transition, these are the rules that move the system from the first state, which is your, to another. If the first state is your, again, the transition rule might say go to the next state when the word is bright. So ang atong na-build the word is your and bright. So the final state, when the sentence is complete, example, your bright pupil was here, the machine reaches its states or final state. Again, how does finite state grammar? First is the states, second is the transition, and the final state. Kung if we're able to build na the sentence, or we were able to complete the sentence, so that is the final states. So that's the way on how finite state grammar works. So in the diagram presentation, figure 9. So the states here, these are presented as circles. Example, state 0, state 1, state 2, state 3, so on and so forth. Each sentence represents a point in the process of generating a sentence. So the transitions, so the state here is this one, this one, this one, this one, this one, this one, and this one. And the transitions here, these are the lines between the states. So these are the lines. These are transitions. Transitions, transition, transition, transitions, transitions. These are the lines between the states which show the movement from one state to another based on the next word. Each transition corresponds specific word in the line. So just like for example, example of transitions here is your bright pupils. Pupils was, where, and here. So that is an example of transitions. Let's proceed. So we're going to break down this figure. Start at the state 0 or O, your. The sentence generation start at the state where the word your is generated. This is the beginning of the sentence. So you're here. So your here is the checkpoint of, or the checkpoint or the beginning of the sentence. So we're going to move to state 1. So the state 1 here, it can be very or bright. So move from state O, your. We're going to move to state 1. It can be bright or very. So you can move state 1 directly and generated the word bright. Or you can move to S1, then make a loop to generate word very, which can repeat multiple times. Very, very is allowed. So after looping through very any number of times, including 0, the machine eventually moved to state 1 with the word bright. So moving to S2, so the S2 here is bright. Again, from state O, the word there is your. So the your here is the checkpoint or the beginning of the sentence. Moving to S1, we choose the word very. And then moving to the state S2, we choose the word bright. It produced, if it is once already, this marks the transition after any repetition of very. The word bright will always appear here regardless of how many times very was repeated. So from the checkpoint your to state 1 bright, or very to state 1 to again state O, or the checkpoint or the beginning of the sentence is your. Moving to the state 1, which is very. Moving to the state 2, bright. Moving to the state 3 and state 3 or 3-4, which mean pupils or pupils. Moving to the state 5. So here's the state 4. State 3, pupils or pupil or pupils. This allowed for the sentence to have either a singular or plural subject. Moving to the state 5, was or were, depending on whether the word generate was pupil or pupils, the machine will move to one of two states to ensure the subject-verb agreement. If state 3, pupil, was chosen, the machine moved to state 5, where the verb was is generated. If you as a person will choose state 4, so pupils was chosen, the machine moves to state 5, where the verb where is generated. Again, we use, for example, so again, we're going to discuss the flow of this diagram. Your here is the checkpoint or the beginning of the sentence. Moving to state 1, it can be bright or very. So let's choose bright or let's choose very. Moving to the state 2, bright. So nanatay sentence nga, you're very bright or you're very or yes, you're very bright. So nanatay na build na sentence, you're from the state 0, move to state 1, move to state 2, you're very bright. Moving to the state 3, pupil or pupils. Nanatay word nga, you're very bright pupil or you're very bright pupils. Now, we're moving to the state 5. If we're going to choose the pupil, your very bright pupil was. And if we're going to choose where, and we're going to choose pupils, your very bright pupils were. So, nanatay na build na sentence. Moving to final state here, after the verb was where is produced, the machine moves to the final states where the sentence concludes with the word here. Your very bright pupil was here. So, naanatay na build na sentence. From state 1, your, state 0, your, or the checkpoint of the sentence or the beginning of the sentence. Moving to the state 1, bright. Moving to the state 2, moving to the state 1, very. Moving to the state 2, bright. Moving to the state 3, pupil. Moving to the state 5, was. So, na-build na nato ang word ni. Your very bright pupil was, and move to the final state here, your very bright your very bright pupil was here. So that's how finite state grammar works. Let's proceed. Example sentences generated by figure 9. So, yan na. The result. Here's how the finite state grammar can generate different sentences. So, your S1 moving to the S1 bright, moving to S2 pupil, moving to S3 was, and moving to, SO here, or the states here, is your. Moving to S1 bright, moving to S2 pupil, moving to S3. Your here is the checkpoint of the sentence. S1 bright, S2 pupil is S3 and S5, and then here, which is the final state. Now so that is an example of simple sentence. Next is the repetition of very. Your very, very, very bright pupil. We're looping. So here's the path. SO, moving to S1, moving to loop of very, to S2, to S3, S5, and the final state. Plural version. Your bright pupil was here. You were here, so that is plural version. These examples are generated from the figure 9. Again, here's how the finite state grammar can generate in different sentences. So next slide, we're going to discuss the input and versus output models of finite state grammar. So input and output models. Input model is the model. Input model. In this model, the grammar reads a sequence of symbol, words, and check if it is a valid sentence. If it encounters symbol that it can handle, there's no transition to a next state. It rejects the sequence as ungrammatical. Imagine you're feeding a machine sentence, and it checks each words one by one. So, to see if it can process it. Again. Imagine you're feeding a machine sentence, and it checks each word one by one to see if it can process it. If it can, it stops. So that is input model. Now the output model. In this model, the grammar produces or generates a sentence by moving from state to state, creating symbols along. It only produces grammatical sequences, and ungrammatical ones are simply not produced. In this case, the machine creates sentences only following the rules that make sense. So, it never creates ungrammatical sentences. Let's proceed to finite state grammar generating sequences. First is the infinite A type of language. Infinite A type language. A string of A's with no upper limit. So in this example, every valid sequence consists of one or more A's. Example A, 2A, 3A, etc. The machine uses a loop to allow any of A's to be generated. This loop means that after generating each A, the machine can go back to generate another A or move to the final state, ending the sentence. So the loop lets the machine generate as many A's as it wants before stopping. So limitation in infinite A type language. It needs a specific rule for the final A to stop the sentence, ensuring it does not loop infinitely. This allows inflexibility in how many A's are generated. So that is infinite A type language. So that is the finite state grammar generate sequences. The first is infinite A type language. Number two is a finite A type language, a string of A's but with an upper limit. Here's the sequence of A's is limited to a specific number, example 1 to 4 A's. Unlike the infinite case, the loop can't be used because it would allow for too many A's. Instead, the machine must follow a fixed path for each number of A's. For instance, one path produces one A, another path produces two A's, or etc. So the challenge in the finite A type language, the machine has to know how many A to produce before starting and must follow the specific path. This makes it less flexible and more complex than the infinite case. So sa infinite A, it needs a specific rule for the final A to stop the sentence, ensuring it doesn't loop infinitely. This allows flexibility in how many A's are generated. While in infinite A type language, the machine has to know how many A's to produce before starting and must follow the specific path. Sorry. So takeaway. Finite state grammar can generate simple repetitive structure like sequences of A's, but they struggle with more complex rules and dependencies, making them less powerful for describing real-world languages. This is why more advanced models like context-free are often preferred. Next is infinite A B type language. So infinite A B type language, this type of language allows any numbers of A's or B's in a sequence. For example, you can have 2A, AB, BB, or any other combination of A's and B's. For example, figure 11 shows a finite state grammar slightly modified to hand the sequence. Finite state grammar manage a combination of A's and B's with a certain complexity. However, the finite state grammar struggles to generate more complicated patterns without modification. Again, infinite A-B type language, this type of language allows any number of A's or B's in a sequence. Next, infinite A-B type language. In this case, the finite state grammar generates strings of A's and B's but with a maximum limit. For example, if the limit is 4, it can generate up to 4 symbols only. This is more restrictive than the finite version, and finite state grammar can handle it with increasing complexity. Infinite A power of n, I don't, please correct me if I'm wrong, B power of n, I think, type language. This language has a string of A's followed by the same number of B's, for example, AAA followed by BBB. A loop would be needed to allow an infinite number of A's and then another loop for the B's. However, there's no way to ensure that the number of B's matches the number of A's in any string. So the conclusion here is that finite state grammar cannot handle this kind of language because it cannot store information about how many A's there are to later match them with the same number of B's. So that is the finite A power of n plus Bn type language. Finite an plus Bn type language. This is similar of the previous one, where there is a maximum limit to how many A's and B's can be in the string. Finite state grammar can handle this type of language but only with great complexity. Figure 14 shows an example of how the maximum number of A's and B's might be limited to 4. The next one, infinite ABBA type language. In this language, a sequence of A's is followed by B's, and then this pattern is mirrored, reversed, to become something like ABBA or AABB. So finite state grammar cannot generate this type of language because it doesn't have the ability to store and later recall the sequence in reverse order. Next, finite ABBA language. The finite version of this language, which limits the number of symbols, can be generated by finite state grammar. But this requires complete structure. Example figure 15 shows how a grammar might work for a limited sequence of symbols like 3 plus 3 symbols. However, this approach is cumbersome. Then the A language, simple sequences of A's aren't very interesting because they only contain one type of vocabulary item, and natural human languages need more complexity involving choices between different meanings. The text concludes that finite state grammar struggle with complex languages that involves multiple items of vocabulary and rules, making them inadequate for most natural human language description. The complexity required for such language exceed what finite state grammar can handle, which makes them significantly flawed for understanding natural linguistic structures. Natural linguistic structures. So that's the discussion of finite state grammar generating sequences. First is the infinite A type of language, finite A type language. Next is the infinite AB type of language, finite, balik-balik, finite niya, I think, finite AB type of language, infinite AN plus BN type of language, finite A and B plus BN type of language, and the last one is infinite ABBA type language, and napadiay, finite ABBA language. Now let's proceed to the application of finite state grammar to English noun phrase. So this figure 16 and 17, this shows how simple sequences of items like words or symbols can be generated by finite state grammar. These sequences are built step by step with the system moving between different states to generate each part of sentence. Wait lang. So that is figure 16 and 17. Again, this show how simple sequences of items like words or symbols can be generated by finite state grammar. These sequences are built step by step with the system moving between different states to generate each part of sentence. Now let's proceed to the figure 18. In this figure 18, a more specific example using English where finite state grammar is used to generate simple noun phrase like the book or the books. This example illustrates how the finite state grammar can handle singular and plural nouns. The modal moves from state O to state 1 when it reads the and then the form S1 to the final state when it reads it either book or books. Next is figure 19. Extends this idea by adding demonstrative like this or this. The finite state grammar moves between different states based on whether the noun is singular, this book, or plural, this books. Now let's proceed today. Finite state grammar can handle more complex noun phrases by introducing various determiners like the, this, enough, and mass noun like and ink. So in figure 20 and 20 and 21. In that figure shows how finite state grammar can combine the word the with demonstrative like this or this to generate phrases like this book or this books or the books. It illustrates how the finite state grammar transition between the different state S2 SO2 to SX, which is the final state based on the word choices. In figure 21 adds determiner like enough, which work with both mass nouns like ink and count nouns like books. It highlights how the finite state grammar can accommodate various combinations by moving through different states. So in figure 22 incorporates more determiners such as such as much used with mass nouns and a used with singular nouns. The diagram shows that finite state grammar can handle a range of combination, ensuring that certain determiner are used only with the appropriate nouns. Example, match ink versus a book. Now let's proceed to the limitation of finite state grammar in handling more complex structures. So, here are some key points. Finite state grammar and complex dependencies. Finite state grammar struggles to generate sentences with complex dependencies, such as nested clauses. Example, if the man that either failed or fell ill complains, then these sentences require certain words or phrases to appear in a specific order, which finite state grammar cannot manage well because it lacks the ability to store information about early parts of the sentence for later use. Another one is the optional elements. Finite state grammar use loops to handle optional elements like adjectives. For example, a loop can insert the adjective new before the pen, but it has limitations. Repeating new many times or inserting additional words like very becomes problematic since finite state grammar would endlessly repeat without rules to stop the loop. So the summary of the finite state grammar limitation: finite state grammar is limited in its ability to deal with non-adjacent dependencies, words that depend on each other but are not next to each other in sentence. Next, optional elements. Optional elements, finite state grammar has trouble handling option words without endlessly repeating them. So that are the limitation of finite state grammar in handling more complex sentence, non-adjacent dependency, and the optional elements. So to sum it up, finite state grammar is a type of finite state grammar is a simple type of grammar that uses a finite number of rules to generate sentences. It operates by moving from one state to another in a sequence, producing grammatical sentences based on transition. However, it has significant limitation. First, sequential structure. It only works well with strictly linear sequence of words or symbols without accounting for hierarchical structures in English, such as phrases within phrases. Second one is inability to handle complex syntax. Finite state grammar cannot account for complex grammatical structure such as nested or embedded clauses that require a more sophisticated understanding of syntax. Next is limited descriptive power. While finite state grammar can recognize some simple patterns, it is not powerful enough to describe the full complexity of natural language, which often require more advanced systems like phrase structure or transformational grammar. A finite state. So that is all about finite state grammar. Moving on to the rewrite grammar. What is a rewrite grammar? A rewrite grammar is a system of rules used to generate complex sentences or language structure. Each rule transforms an initial symbol like Z into a sequence of symbol which can be further rewritten until they become a final string or terminal symbol like words or letters. Rewrite grammars are more powerful than finite state grammar because they can handle more complex language structures, including recursion and nested dependencies. So, component of rewrite grammar. Rewrite grammar is more powerful than finite state grammar for several reasons. First, terminal and non-terminal symbols. So, these are the components of rewrite grammars. Terminal symbol, these are the actual words or symbol in the language. Example A, B. Next is the non-terminal symbols. These are intermediate symbols that help break down the structure of sentences like categories or parts of speech. Example, noun for noun phrase, that for determiner. So, rewrite rules relates this symbol by transforming non-terminal symbol into terminal symbol or other non-terminal symbols, guiding the sentence formation process. So, components of rewrite, again, this is the continuation of the components of rewrite grammar. Number 2, rules. Rewrite rules look like W followed by X, where W is transformed into X. This is the core of how rewrite grammar operates. Rules can be as simple as replacing a non-terminal with a terminal symbol, or as complex as combining multiple symbols to generate a specific rule. Number 3, recursive nature. This is the number 3 of components of rewrite grammar. Recursive rules allow sentences to be expanded indefinitely by reapplying the same rule to itself. This is crucial for generating sentences of infinite length, like nesting clauses. For example, a rule like noun phrase transform into noun phrase plus verb phrase allows the recursion needed to build complex sentences with multiple clauses. Next is flexibility. As seen in the example on the page, W, close parenthesis plus X, to Y plus Z, rewrite rules are flexible and allow for optional elements noted by the parentheses, enabling them to model different syntactic structure or a language. This flexibility is important for describing natural languages, which can have varying word orders or optional parts of speech. So, here are the components of rewrite grammar. First is the terminal and non-terminal symbol. Rules. Number 2, recursive nature. And lastly, the flexibility. So, advantages over finite state grammar. Number 1, handling complexity. While finite state grammar can generate sentences by moving between a limited number of states, it struggles with more complex patterns. In contrast, rewrite grammar can handle hierarchical structure. Example, embedding one clause inside another and along distance dependencies, which are common in natural language. 2, non-terminal symbols. Non-terminal symbols in rewrite grammar allow it to store intermediate
stages of sentence generations, enabling the grammar to break down and analyze sentences more effectively than the finite state grammar. Number 3, more powerful rules. Rewrite grammar allows for more sophisticated rules such as generating multiple terminal symbols at once or creating purely non-terminal sequences that build up complex phrases. Example, non-phrase to determiner plus noun. Example, the page provided where S1 followed by A plus B plus S2 allows the grammar to generate sequencing containing A followed by B before transitioning to another state. State 1 followed by state 1 to A followed by B before transitioning to another state. This flexibility makes rewrite grammar more powerful for modeling language that have more complicated sentence structures. So the power of rewrite grammar. Rewrite grammar involves rules that specify how one set of symbols, often non-terminal symbols, transform into another set, eventually yielding a terminal string composed only of terminal symbol. Excuse me. And next, each rule has form like Z replaces A followed by B, where a symbol like Z is written into two or more another symbol. So in the rewrite grammar, each rule has form like Z can be written by A plus B. So the initial symbol here is Z in this case. Z is the start process. And the symbols on the right hand side are applied through a sequence of rewrite rule. Z can rewrite into A followed by B until a final string until a final terminal string is achieved. So in rewrite grammar, here's an example. So in this example for the grammar, Z replaces A followed by B, A replaces M, A replaces N, B replaces P plus Q, B to R. The initial symbol should be Z. So always remember, Z here is the initial symbol. The non-terminal symbols A and B, and the terminal symbols M, N, P, Q, R. So the possible derivation giving the real number in the parentheses would include. So, sorry akong na kuris-kurisan. Z replaces A. So we replace A to A plus B. Next, applying the rule number 2, we replaces A to M. Again, so Z here is the initial symbol. We're going to apply the rule number 1. Z replaces A plus B. So applying rule number 1, we're going to replace A as Z to A plus B. So here's the result of rule number 1. Now, we're going to apply the rule number 2. How come the result here is M plus B? So, the initials, we're going to replace A, according to rule number 2, we're going to replace A into M. So, the result here is M plus B. Here's the result, M plus B. So, ngano daw nga naay result nga M plus B? Kay, atong gi-replace ang A into M, and the result is M plus B. Next, here, in this category, Z. Z is the initial symbol. So, the non-terminal symbols are A and B, and the other terminal symbols are M, N, P, Q, R. So in rewrite grammar, the initial symbol here is letter Z. So the in rewrite grammar, the initial symbol would be Z. So we're going to apply the rule 1. Z replaces A plus B. So here is the rule number 1. Now, applying the rule number 5. So we're going to apply the rule number 5. We replaces here P into R. So in this first rule, we apply B, or we changes B into R. So the result is A plus R. Next, N plus R. N followed by R's. We're going to apply the rule number 3. We replaces A here into R. So rule number 3, we replaces A replaces N. So A replaces N plus R. So the result is N plus R. So that is how the rewrite. So that is the way on rewriting a grammar. So here, non-terminal versus terminal symbol. Terminal symbols are intermediate symbols that get rewritten according to the rules. Terminal symbols are final symbols that don't get rewritten further, representing the vocabulary of the language. The rule apply step by step, leading from non-terminal symbols to terminal one. For example, from Z replaces A plus B. Pwede daw na to alisdan ang Z o A or B. So the non-terminal symbols A and B may themselves get written according to the other rules, and their terminal symbols are rich. So ang kanina mga results, these are the terminal symbols. Mao ni ang result from initial symbol to non-terminal symbol to terminal symbols. You can ask question after my report. Next, we're going to continue. So derivation here. A derivation refers to the sequence of transformation from the initial symbol to the terminal string. 'Di ba? From initial to non-terminal to terminal string, ang process nga gitawag dito is derivation to siya. Derivation refers to the sequence of transformation from the initial symbol to the terminal string. And the result of derivation is what we call terminal string. This process can have multiple possible paths depending on the choices available. The page given an example grammar with several rules and shows how different derivation can lead to different terminal string. The derivation might include string like M plus P plus Q plus M plus R, N plus Q, P plus Q, or N plus R. So in our recursive rules, now let's proceed to the recursive rules and infinite generation. Some rewrite rules are recursive, meaning they can apply repeatedly, allowing the generation of infinite strings. For instance, the rule Z replaces A or ZA allows infinite sequences of symbol A. And this is because Z can either be written as a terminal string, or recursively as ZA, generating progressively longer string of A's. So types of language in rewrite grammars. Infinite A-type language. This language allows any sequence of letter A ranging from 1A to an infinite number of A's. It is generated by the recursive rule Z can be written to A or ZA, where Z can either be written as single A or as ZA, which means Z can repeat the process of adding more A's indefinitely. This covers all possibilities of finite state loops. Next, finite A type language, maximum of 4 A's. Here, the sequence is limited to a maximum excuse me, of 4 A's. The rule used here would look like Z can be written to A, or AA, and continuous until the maximum of 4A is reached. It can be written as A. I don't know how to read. Basta in this indefinite A type language, it can be read. The sequence is limited to a maximum of 4. So infinite AB type language. This language allows any sequence of A's and B's in any combination. It generated by the rule Z can be written to AB, which allows for any sequence of these two letters. Infinite AB type language. Next is the finite AB type language, maximum of 4 A's and B's. This language has limit number of 4 A's and B's. It can be generated using a more complex rules such as ZAAAB to ensure that the number of A's and B's stays within the limit. Next, infinite AN plus BN type language. This language requires an equal number of A's followed by an equal number of number of B's. A rewrite grammar can easily generate this with a simple rule Z to A close parenthesis B, which ensuring that for every A there is a corresponding B in the string. Next, finite AN BN type language, maximum of 4 A's and B's. This language requires the number of A's and B's be the same with a maximum of 4. The rule to generate this language is Z can be written to A, B, B, B. Next is the infinite mirror image type language. This language has sequence like ABBA where the string is mirrored. It is generated by the rule Z can be written to A, close parenthesis ZA, B, close parenthesis Z, B. Next is the finite mirror image type language. A finite version of the mirror image language is generated similarly, but it's limited to a maximum of 6 symbols. The process is complex due to conflating everything into a single rule, but it essentially follows the same pattern as the finite version. Next, rewrite grammar. Again, that are the type of language in rewrite grammar. Infinite A type language, finite A type language, maximum of 4 A's, infinite AB type of language, infinite AB type language, maximum of 4 A's and B's. Next is infinite A power of N plus B power of N type of language, infinite AN plus B power of N type language, maximum of 4 A's and B's. Next is the infinite mirror image type language. Lastly, the finite mirror image type language. Now let's proceed to rewrite grammar for noun phrase. The text discussed the generation of noun phrase using a rewrite grammar. A finite state pattern, like in the previous example, can be converted into rewrite rules. For instance, SO can be written much leads to another states S1. S1 to ink, this data directly produces the noun ink. Other example includes rules for determining like this, the, or which lead to either singular or plural nouns. Example, books, inks, etc. Excuse me. So, simplification. Instead of using non-terminal symbol S1, S2, etc., we can combine them directly into simplified rules. So, S, much ink, to enough ink, a book, this ink, these books, the books. This shows how we can generate correct sequences using simpler rules that eliminate intermediate. Next, we're going to discuss the unrestricted rewrite group. These grammars are very powerful, like Turing machine, meaning they can theoretically describe any sequence or system that follows clear rules like this game or political outcomes. Next, the problem is that unrestricted grammars are too general and don't consider the constraints that language naturally follow, such as related words appearing together. They can generate correct structure but aren't useful in assigning grammatically labels correctly. So that's that's my report in rewrite grammars. To sum it up, rewrite grammar generates sentences by using rules that replace symbols with words or other symbols step by step. It allows for complex structures by applying these rules repeatedly, often visualized through tree diagrams. Unlike simpler models, rewrite grammar can handle nested and recursive language patterns, making it more suitable for natural language. Now let's proceed to phrase structure grammar. So phrase structure grammar focuses on generating sentences by specifying their internal structure step by step. It uses non-terminal symbols which represent grammatical categories like determiner, means that, and noun, to define how a phrase is built. Instead of generating a phrase like the book all at once, it breaks the process into smaller steps. A noun phrase can be written into determiner plus noun followed by noun. This shows the noun phrase is composed of a determiner and a noun. Determiner composed of the, my, any. Again, her determiner can be one of several options like the, my, or any. So the noun, book, books, ink. Similarly, the noun can be books, book, or ink. So, the process of generating sentences using labeled tree diagrams. So, labeled tree diagram symbols, example, NP or for noun phrase, represent grammatical categories. The diagram shows sequential relation left to right and constituency relation top to bottom, illustrating how part of a sentence fit together grammatically. In rewrite rules, sentences are generated by applying rewrite rules where one symbol, example, noun phrase, is break down into another symbol, example, determiner plus noun, where determiner equals or that is equal to determiner. Example, noun phrase to determiner plus noun, or determiner to my and noun to ink. Derivation history, each step of sentence generation is recorded, creating a history of the applied rules. In this example, my plus ink is derived from the determiner, noun, is derived from determiner plus noun. So, my plus ink is derived from determiner, noun. Determiner plus noun. So, in that figure, that is an example of tree diagram. So, tree diagram representation. The diagram is built step by step, starting with the initial symbol, example, noun phrase. So again, the diagram is built step by step, starting with the initial symbol, noun phrase, here at the top. As each rule is applied, new symbol replaces the old one, forming the branches on the tree. The final three visually represent the sentence grammatical structure here. The final three. The diagram in the example shows the phrase my ink with a determiner. Determiner here is my, and the noun here is ink as the branches of noun, phrase. So that is tree diagram representation. Next, nod. This is a continuation of the tree diagram representation. Each label in the tree diagram, example, noun, phrase, noun, name, is called a nod. This one. A nod connects to other symbols lower in the hierarchy and represent the relationships. Nod. Shared syntactic characteristic of nod. The use of identical nods like nod phrase from my ink and John shows grammatical function. Even if they continue different types of elements, noun phrase versus a proper noun, this means both phrases have the same syntactic function, even represent different types of objects. And tree diagram consistency, the tree diagram remains the same regardless of the specific order as long as the structure adheres to the overall grammatical rules. This is because the tree captures the essential structure, not the individual step. So, rewrite rules and restrictions. Restriction 1. Only one symbol should be replaced in any given rule. This is to prevent confusion about which nod, the higher level symbol, new symbol should connect to. Example of individual rules, A, B can be replaced to C, D, E. Multiple replacement, making the diagram unclear. For example, determiner plus noun to art plus adjective plus count name also replaces multiple parts in a single step, which violates the rules. So, again, we should always remember in rewrite rules and restriction. Restriction 1, only one symbol should be replaced in any given rule. Now, Now, let's go to the rewrite rules and restriction number 2. No symbol should disappear without being replaced. The rule no symbol should disappear without being replaced means that symbol must be consistently replaced by other symbols, ensuring that the tree remains complete at all stages. Zero symbol. A zero symbol can be used as a placeholder when a symbol is removed without replacement. Example. Rules like ABC replaces AB where C is disappear as considered invalid. Similarly, determiner plus noun to that would give an acceptable output like any, being left dangling without a corresponding noun. So zero here in a zero symbol can be used as a placeholder when a symbol is removed without replacement. Again, there are two rules, rewrite rules and restriction. One is only one symbol should be replaced in any given rule. Number 2, no symbol should disappear without being replaced. So the zero symbol here can be used as a placeholder when a symbol is removed without replacement. Now, let's proceed to phrase structure grammars and their ability to handle restriction on combination of different grammatical subclasses. First is the phrase structure grammar versus the finite state grammar. Phrase structure grammar are more restrictive than unrestricted rewrite grammar, making them more suited to handling natural human languages. They are also more powerful than finite state grammar, which struggle to generate all aspects of a language. So number 2, noun phrase subclasses. The section provides an example of English noun phrase such as this book, that book, and this book, showcasing the needs to account for restriction on co-occurrence of determiners and nouns. So determiners, example, this, and nouns. Example, book, books. need specific rules for combination to avoid ungrammatical output like this book or those page. Next, rules for combination. The rules provided outline how singular and plural determiners, that, singular, determinal, plural, and noun, non-singular, non-plural, combine to form an acceptable noun phrases. Example include noun phrase to determiner singular plus noun singular. Example, this book. So the next is noun phrase, determiner plural plus noun plural. Example, this books, this books. Next, oh my god. Now let's proceed to the limitation of grammar. The partial grammar provided doesn't explicitly state that singular and plural determiners or nouns share common grammatical properties. It only generates two distinct types of noun phrases, lacking a deeper grammatical insight into their shared features. This is pointed out as a potential flaw, as intelligent readers may assume a connection between singular, plural determiners and noun that the grammar fails to make explicit. Now let's proceed to the concept of context-sensitive grammars and introduces the concept context-sensitive rules. Now, context-free versus context-sensitive rules. If we say context-free rules are rules that can be applied regardless of the context in which a symbol appears. For example, a context-free rule can rewrite a symbol anywhere in the sentence without considering its surroundings. Context-sensitive rules, while context-sensitive rules are different. These rules specify that a symbol can only be written within a certain context. For example, a rule might state that a particular symbol can only be written if it is preceded or followed by a specific symbol. So that is the difference between the context-free and the context-sensitive rule. Now, we're going to discuss in formulating context-sensitive rules. The text provides a notation for context-sensitive rules, such as rewriting a symbol x into y plus z, but only when x is the context of p and q. It is surrounded by p and q. This formulation ensures that the rule applies only certain structural position or when specific symbol are adjacent to being written. So that is formulating context-sensitive rules. Now, we are going to proceed the hierarchy of grammars. The text outlines a hierarchy of grammar based on restrictiveness. Finite state grammar are the most restrictive. Context, phrase, structure grammars allow more flexibility. Context-sensitive phrase structure grammar permit even more flexibility by incorporating context-sensitive rules. Unrestricted rewrite rule grammars are the least restrictive and can generate more complex structures. Now let's proceed to the application of context-sensitive rules. The text suggests applying context-sensitive rules to solve specific grammatical challenges. For example, you might need to enforce that certain elements, like determiners and noun, most co-occur in specific ways, which can be handled when context-sensitive rules. So, here are some background of context-sensitive rules. Rules example. A set of rules is presented to describe how determiners, example, this or this, and nouns, how determiner and noun, example, book or books, combine based on number of agreement. It can be singular or it can be a plural. Now, in tree diagram, this show the structure of noun phrase like this book or this book with nods labor for determiner and noun, reflecting how the grammar identifies the relationship between singular and plural. So in the context-sensitive rules, these rules allow the grammar to handle such agreements effectively by specifying when to apply certain forms of determiner and noun depending on context. In general application, natural language requires extensive use of context-sensitive rules to address various phenomena, such as subject-verb agreement or grammatical case. Example, how nouns change when used with different preposition or verbs. Now, in context-sensitive rules, in reformulation of rules, the explanation also touches on how context rules can specify multiple conditions, example, singular, plural, and use a default elsewhere rule for all other cases. Again, this is a continuation of the context grammar, sensitive and context rules in grammar. Elsewhere element, this, if we say elsewhere element, this is typically the singular form of a noun considered unmarked because it lacks a plural suffix. Now, it is used in a wide range of contexts and occurs by default when grammatical number doesn't apply. Rule comparison. Rule 1 is a constituency rule. Defining the structure of noun phrase. Example, determiner plus noun. Rule 2 is a subclassification rule, which distinguishes between subclasses like singular and plural nouns. Next, branching. Subclassification rules gives to arise the unitary branchings where one choice is selected without being a true part of the higher structure. Lastly, optional elements. Some rules involve optional elements. Example, verb plus adverb. These are shown with parentheses and blend constituency and sub-classification. Additional rule types and the adequacy. Next is the additional rule types and the adequacy of phrase structure grammar. So this will be the last slide of my reports. First is in additional rules. Additional rule types and the adequacy of phrase structure grammars. First is the verb complex rule. This rule describes a required verb with an optional verbal adverbial like an adverb attached. It is important not to misinterpret this as giving a choice of having verbs since the verb is compulsory. Next is the lexical realization. These are rules that introduces specific symbols or lexical items such as this or book. These rules differ from the classification rules discussed earlier and are called terminal rules because they directly introduces words in the grammar. Lastly, the syntactic pictures. Another difference in rule type involves subclassification based in the syntactic rules like common versus proper noun or countable versus uncountable nouns. So here's the summary of phrase structure grammar. Phrase structure grammar is a type of generative grammar that explains how sentences are built by breaking them into smaller hierarchical parts. It works through rules that combine noun phrase, verb phrase, and other elements to form sentences. Each sentence can be represented in a tree diagram where the sentence structure is shown step by step from its highlight level to its individual words. So here are some key features of phrase structure grammar. Hierarchical structure, it breaks sentences into a layer of components, showing how smaller parts like nouns, verb, and phrase work together to form a full sentence. Tree diagrams. The sentence structures is often displayed using tree diagrams, which is illustrate the relationship between the different parts of the sentence. Example: subject, verb, object. Rules. The grammar is based on rewrite rules such as sentence to noun phrase plus verb phrase, where a sentence is made up of a noun phrase. Again, here are some key features of phrase structure grammar. First one is the hierarchical structure. Second one is tree diagram. Third one is the rules. The grammar is based on rewrite rules such as sentence to noun phrase plus verb phrase, where a sentence is made up of a noun phrase and a verb phrase. These rules can be applied recursively to generate complex sentences. Next is the descriptive power. Phrase structure grammar explains how sentences are formed but has limitation when it comes to explaining certain sentence transformation, like turning active sentences into passive one. Limitation: while it's more powerful than finite state grammar, phrase structure grammar struggles with more complex linguistic patterns, like discontinuous elements where related parts of a sentence aren't next to each other, and transformations, example, passive voice or question formation. So in summary, phrase structure grammar is a useful model for describing how sentences are built from smaller components, providing a clear, hierarchical structure for understanding language. However, it requires additional rules like transformational grammar to handle more complex sentence structure and transformation. We were going to discuss the last part of generative grammar, rules and description. So the last part is the adequacy of phrase structure grammars. So let's start. There are two main challenges that phrase structure grammars face. The first one is transformationally related structure. So these are structures like active versus passive sentence, sentence versus nominalization, or unmarked versus cliff subject forms. Each pair of sentences has the same core meaning but differs in their surface structure, making it difficult for phrase structure grammars to account for these transformations. So that is transformationally related structures. The second one is the discontinuous constituents. This present challenges because phrase structure grammars rely on tree diagrams, which are limited to showing adjacent relationship between elements. The limitation makes it hard to represent cases where elements that are not next to each other in the sentence are related. So, those are the two main challenges that phrase structure grammar face. First, transformationally related structure, which means these are the sentence form that share the same meaning but differ in how they are structured. And just like active to passive, sentence versus nominalization, or unmarked versus cliff subject. Phrase structure grammars struggle to explain this transformation because they focus on the surface structure. So in transformational related structures, these are the sentence forms that share the same meaning but differ in how they are structured. Now, in the discontinuous constituents, these are sentence elements that are related but not next to each other. Related but not next to each other. Phrase structure grammars which rely on three diagrams showing adjacent relationship find it hard to represent these cases where the related parts of a sentence are separated. These difficulties suggest that phrase structure grammars may require transformational rules or other tools to handle complex sentence relationships that go beyond adjacent elements or simple sentence form. So that are the two main challenges that phrase structure grammars face. Again, the transformational related structure and the discontinuous constituents. Now let's proceed to the next slide. The two kinds of rules used in grammar. The first one is the phrase structure rules. These are the basic rules that help us build the structure of a sentence. For example, John wakes up as a clear structure. So, the subject John plus verb wakes plus adverb up. So, these are the basic rules that help us build the structure of a sentence. For example, John wake up has a clear structure. The subject is John plus the verb wakes plus the adverb up. These rules will work well for most simple sentences. Now let's go to the second one of rules used in grammar, the transformational rules. These come into play when we need to change the structure of a sentence but keeping the meaning the same. For example, we can change John wakes up into wake up John. We can change John wakes up into wake up John without changing the meaning. So that is transformational rule. This change is done by a transformational rule. If we say transformational rule, we need to change the structure of a sentence but keeping the meaning the same. So here's the issue. Phrase structure rules alone can't explain all sentences. Some sentences are more complicated and involve deeper relationship between words that aren't obvious just by looking at the sentence. For example, in Wake Up John, the deep structure which explains the relationship between words is different from the surface structure, what the sentence look like when spoken. This is where we're going to apply the transformational rules help. They explain how we can take one sentence and transform it into another version, like turning John wakes up into wake up John while still keeping the meaning intact. So in short, phrase structure rules help create basic sentence structures, while transformational rules help explain how different sentence forms are related even if they look different on the surface. Now, in the next slide, we're going to discuss the complexities of grammar, especially the difference between surface structure, what we see or hear, and deep structure, the underlying meaning or grammatical relationship. So, in the transformational rules in grammar, transformational rules are used in generative grammar to show how different sentence structure with the same meaning are related. So these rules help us understand how different version of a sentence, like Cromwell took the castle and the castle was taken by Cromwell, are
essentially expressing the same idea but look different. So now, we're going to discuss the deep versus surface structures. Now, if we say deep structures represent the core meaning of a sentence, while the surface structures are the actual sentence we speak or write. Additionally, transformational rules relate these two structures, helping us understand how one deep meaning can result in multiple surface sentences. So here's the question. Why do we need transformational rules? Some important parts of the meaning or deep structure don't show up in the actual sentence surface structure. For example, in a question like, do you like pizza? The word do doesn't add new meaning but helps form the question. These rules also control the order of words. For example, John will eat. John will eat. So that is a normal order. The second one is the will John eat. So that is question order. So that are the reason why do we need transformational rules. Now, the next slide is we're going to discuss the problem with phrase structure rules alone. Phrase structure rules, basic rule that tell us how to combine words like noun plus verb, are enough to explain all the complexities of the language. Also, the transformational rules are needed to account for different sentence forms and ensure that sentences make sense in both meaning and structures. So that are some problem with phrase structures rules alone. So there are some challenges of combining the two. So combining phrase structure and transformational rules create a grammar system that is powerful. But this system may become too flexible, allowing too many sentence form, making it difficult to explain language clearly. So that is the challenge of combining the phrase structure and the transformational rules. Linguists are faced with the challenge of creating a grammar model that is flexible enough to describe all possible sentences but precise enough to be useful for understanding how language works. So that are the challenge of combining the phrase structure and transformational rules. And the next slide, we're going to discuss the grammatical analysis of the same sentence. John kissed Mary yesterday. So in figure 27, Chomsky, 1957. So in that example or in that figure, this tree uses a basic phrase structure grammar to break the sentence down into its major components. So the subject here is John. The verb phrase here is kissed Mary. And the time reference is yesterday. So the auxiliary verb ed for past tense is placed under the category of verb. So in this figure, Chomsky used basic phrase structure grammar to break down the sentence, down into its major components.
So it shows a straightforward surface level relationship between the elements of the sentence. Now let's proceed to the next slide. So again, we're going to analyze this same sentence, John kissed Mary yesterday. In figure 28, Chomsky 1965, these diagrams add more detail to the sentence structure by introducing the predicate phrase. It separates the auxiliary and the verb more clearly and distinguishes between subject noun phrase for John, and predicate verb phrase for kissed Mary, and the adverb yesterday. So it separates, so in this diagram, it adds more detail to the sentence structure by introducing the predicate phrase. So the predicate phrase here is the predicate phrase here is the verb phrase kissed Mary. It separates, again, in this figure, this diagram or tree diagram adds more detail to the sentence structure by introducing the predicate phrase. It separates the auxiliary and the verb more clearly and distinguishing between subject, which is the noun phrase for John, predicate, which is the verb phrase for kissed Mary, and the adverb yesterday. This reflects our more refined understanding of sentence structure. Now let's proceed to the figure Fillmore 1968. This tree introduces even more layers of the structure, particularly distinguishing between modality, the tense related to tense and time, example yesterday, and the preposition, the core content of the sentence, example John kissed Mary. The sentence is split into two major components, modality, time and tense, and proposition, who did and what to whom. So in that figure reflects an even deeper analysis of sentence elements, focusing on both time and agent action relationship. So that is according to Fillmore 1968. Now, we're going to discuss the descriptive adequacy as a long-term objective. It is the continuation of the sentence John kissed Mary yesterday. The descriptive adequacy as a long-term objective. The goal is to find methods that account for both the structure and the meaning of the sentence in a way that reflects how humans understand and generate language. Descriptive adequacy involves recognizing how different sentence structures convey different meanings even when the surface structure looks similar. So if we're going to compare figure 28 and 29, figure 28 handles the structure of transitive verbs with the direct object like kiss, but struggle with intransitive verbs that don't need an object like sleep. In a figure 29 can better explain how certain structures are interchangeable, example John kissed Mary, versus Mary was kissed by John, reflecting deeper grammatical relationship beyond just surface level challenges. Excuse me. Let's continue the last part, challenges in grammatical description. It's hard to select a single correct
grammatical structure because various structure might describe a sentence in different, equally valid ways. Additionally, the text suggests that the best approach is to aim for descriptive adequacy over time by exploring different groupings of sentence elements and determining what count as a valid grammatical rules. So that is the challenges in grammatical description. So that is the last part of the adequacy of phrase structure grammar. So if we're going to summarize, phrase structure grammar is more powerful and restrictive than finite state grammar, offering the ability to generate various kinds of sentence while maintaining both observational adequacy, generating all possible sentences, and descriptive adequacy, assigning proper grammatical description. However, despite its advantages, phrase structure grammar alone is not enough to describe all aspects of human languages. So, these are the specific challenges such as transformational related structure. This includes variation like active versus passive or noun versus verbs. For example, Cromwell took the castle versus the castle was taken by Cromwell. Phrase structure grammar struggles to account for this change fully. Now the second one in specific challenges. Discontinuous constituent elements in a sentence that are related but separated by other words or phrase present a problem for phrase structure grammar as it is focuses on adjacent relationship between sentence elements. Due to this limitation, phrase structure grammar must be supplemented with transformational rules. So these rules help relate deep structure, the underlying meaning of a sentence, to surface structure, which means the way a sentence is presented. So transformational rules resolve issues such as deep structure without surface realization, elements in deep structure that are absent in the surface structure, and poor sequencing of sentence elements. So, in conclusion, while phrase structure grammar is essential for generating sentences and ensuring observational adequacy, it needs additional transformation rules to fully achieve descriptive adequacy and effective model complex sentence structure struggles in human language. So that's all, and thank you.